Now that you all have mastered synthesis reactions and decomposition reactions, it's time to move on to our next reaction, which is called a single replacement or single displacement reaction. You hear it said both ways. I think your book might say single replacement. You might hear me say displacement. Anyway, it just kind of depends where you are and what textbook you have. So you can use those words interchangeably, okay? But single replacement kind of gives you a little bit of idea of what's going to be happening here. So in a single replacement reaction, basically one thing is going to switch places with another thing. So if we're just using simple letters here, in this case, A is going to switch places with B. Notice A is by itself and B is bonded to C. Well, if A and B switch places, then B is going to be by itself and A and C are going to be together. Okay, so let's take a look at what that would look like with some actual elements. Here we go. Here we've got two metals switching places. So here we go. We've got aluminum and nickel. And since aluminum is a metal, it's going to switch places with another metal. Okay, so this is the rule. Metals switch places with metals, non-metals switch places with non-metals. So here we have a metal by itself. So it's going to go in and it's going to kick this other metal out. So now this other metal, which happens to be nickel, is now by itself. And now the aluminum gets to buddy up with the chlorine. Okay, so notice first aluminum is by itself. And then nickel's with chlorine, and afterwards nickel's by itself and aluminum's with chlorine. So these two just swapped places. One replaced the other. Okay, now one thing to pay attention to here is this Cl2 is because nickel is +2. Okay, but over here aluminum is +3, which is why it's Cl3. Okay, so don't forget our subscripts are written because of charges. All right, so you have to keep charges in mind here when we're dealing with ionic compounds, okay? So aluminum, nickel, metal changes place with metal. Of course, that wasn't balanced, so let's just get a little practice there. Right off the bat, hopefully you can see that chlorine is what is not balanced. We have a 2 and a 3. Uh-oh. Hopefully by now you know when we got 2s and 3s, the only way they can balance each other out is when we get them both equal to 6. So I put a coefficient of 3 here because 3 times 2 is 6. And I put a coefficient here of 2 because 2 times 3 is 6. But in fixing my chlorines, now I've messed up my nickel and my aluminum because this 3 here applies to everything behind it. So this means I also have 3 nickels, which means I got to put a 3 here. And this 2 means I also have 2 aluminum. So I have to put a 2 here. And now everything's balanced. Let's take a look at another example of a single replacement reaction. Here are some nonmetals trading places. So notice that the thing by itself here is one of our nonmetals. It's a halogen. Okay, so we got a halogen by itself. Now, why is it not by itself? Remember, because it's diatomic, right? Okay, but that's as by itself as it gets. So we have just fluorine with potassium chloride, and now this fluorine is going to come, it's going to kick chlorine out because chlorine's the other nonmetal, and now chlorine's going to be by itself, okay, but of course it's never really by itself because it's a diatomic, and now fluorine is going to take its place and be bonded to the calcium. So again, fluorine and potassium switch places, and they both have little 2's because they are both diatomic. So again, nonmetal changing place with a nonmetal, and of course nonmetals are always written second in our ionic compound, which is why it's not FK, but it's KF because the metal always comes first. Here's another example. This time we're just using a polyatomic ion. Now, sometimes people, you kind of freak out when you start seeing extra, letters and symbols. Don't get freaked out. It is the exact same thing. So here we have a metal by itself, which means it's going to be looking for a metal that's in a compound. So just because this huge thing is like all big and long, don't get freaked out. All this means is the zinc and the iron are going to change places, and now iron's going to be by itself, and the zinc is going to be buddied up with this SO4. Okay, now as it turns out, SO4 is sulfate. It's off our, polyatomic ion sheet, and it is a -2, and zinc is always a +2. So these go together 1 to 1. Excellent. But over here, as it turns out, this iron is +3. If we look on our periodic table, the 3 is in bold. So I know it's the +3 kind. Sulfate is -2. So the only way to get 3 and 2 together are to be making to 6, right? This is kind of where we can use our crisscross applesauce rule here. So we trade it up. And so we've got 2 irons because 3 times 2 is +6, and we have 3 sulfates because 3 times -2 is -6. Okay, so that's where those little numbers come from. But don't get freaked out. It's just this zinc and this iron switching places. Now the iron is by itself, right? The iron has been replaced by zinc in our compound, and now iron is all by itself where zinc used to be by itself. Again, metals can only change place with metals, okay? So we would never have this zinc and this iron bonded together at the end of it. Nope, they can't, okay? So the metal is going to change places with the metal, and so then we'll still have a metal by itself at the end. And just, it's always good for balancing practice. If we look, we have 2 irons here and only 1 here, so I can put a 2 there, okay? So that's where that 2 comes from. And then notice I have this little 3 after SO4, which means I have 3 SO4 clusters. So the way to fix that is I got to put a big coefficient of 3 in front of my Z and SO4, but that also then now gives me 3 zincs too, so I got to put a 3 right here, and now it's balanced. So you've now just seen 3 different examples of single replacement reactions. One where a metal replaces a metal in a regular old ionic compound. One where a non-metal replaces a non-metal in a regular old ionic compound. And one where a metal replaces a metal, but this time there's a polyatomic ion in there. Okay, so we'll be doing lots more practice with this at class, and hopefully you got these examples copied down.